All right, so here we're going to introduce some concepts related to chemical energy. This chapter is all about thermodynamics. Thermo is the Greek prefix referring to heat. So, really, we're talking about heat energy here. And dynamics refers to kind of how that heat flows. So, thermodynamics is the study of energy flows. Here, we're specifically looking at thermochemistry, the study of heat flow and chemical reactions. Whenever we think about chemical energy, we have to think about the system versus the surroundings. This is a big idea in thermodynamics that we have the universe, and the universe is everything, and everything consists of the system, which is whatever you're looking at, and then the surroundings, which is the rest of the universe outside of that system. So the system is the matter being investigated, whatever it is. And most of the time in this class, the matter being investigated is going to be a chemical reaction. It doesn't have to be a chemical reaction, but most of the time that is going to be what we're talking about, at least in this class. So the chemical reaction is going to be your system that you're investigating. And you're interested in the changes that that system undergoes in going from whatever the initial state is to whatever the final state is. So in the case of a chemical reaction, the initial state would be the reactants on the left side of the arrow. The final state would be the products on the right side of the arrow. And as that chemical reaction proceeds from the initial to the final state, you have energy transfer occurring between the system and the surroundings. So we need to look at whether heat is flowing out of the system, whether heat is flowing into the system, how is energy flowing in the chemical reaction. And remember, the system is the matter being investigated, and the surroundings is just the rest of the universe. It's everything else. So the universe is everything. The universe is defined as the system plus the surroundings when we're talking about thermodynamics. So the universe is the system plus the surroundings. So we're interested in looking at how did the surroundings influence the system and vice versa. How does the system influence the surroundings? So in this chapter and in the future as well, we're going to talk about several thermodynamic state functions. Now, state functions are refer to properties that they're always denoted with a capital letter. And they refer to properties for which only the initial and final states are considered when we think about how that state function changes in value. So whenever you have a big capital letter referring to a property, that tends to be a state function. For example, volume. Volume is given by a big capital letter V. Pressure would be another one, big capital letter P. Temperature would be another one, big capital letter T. Pressure, volume, temperature, all of these are state functions. And the definition again is that in a state function, only the initial and final states are considered in how that state function changes in value. Let's give an example with volume. If the volume of a gas increases from 1 liter to 2 liters, can we figure out the delta V, the change in the volume? So to figure out the change, we need to take the final state, whatever it is, I'm going to call that the final volume, and subtract the initial state, so V initial. Okay, so V final minus V initial gives us delta V, the change in the volume. So if we read what happens, the volume of the gas increases from 1 liter to 2 liters. The 1 liter is the initial state, and the 2 liters is where it ends up. That's the final state. So the final state is 2 liters. The initial state was 1 liter. The delta V, therefore, is 2 minus 1, or 1 liter. So delta is the change in volume. And you can calculate the change in value for any state function going from the initial state to the final state. Now, what we're going to do most often in this class, in this chapter, is look at energy changes in chemical reactions. Let me give you an example of the kind of reaction we might look at. If hydrogen gas reacts with oxygen gas, we make water. So here's the balanced reaction. 2H2 plus O2 makes water. This is the combustion of hydrogen gas. So if we think about this, the reactants, everything on the left side of the arrow, have some kind of energy to start out with. And the products, so these 2 moles of water here, have some kind of energy themselves. So often we're interested in seeing how energy flows in chemical reactions. So the delta E for this reaction would be equal to the energy of the products minus the energy of the reactants, because the products are the final state and the reactants are the initial state. So this is a situation in this chemical reaction where the products are lower in energy than the reactants. So the water is lower in energy than the hydrogen and the oxygen. That means that as this reaction proceeds from left to right, energy is released in the form of heat. So what happens is we start out with the reactants, which are very high energy, and as we convert to products, the products are lower in energy, and the difference is released as heat. So heat is kind of a non-chemical product of this reaction. Heat is released in this reaction. When heat is released, okay, when heat comes out, we call that an exothermic reaction. So exo means out, therm is heat. So when heat comes out of the system, we would call that change exothermic. Okay, whenever you have heat coming out, that would be an exothermic reaction. The opposite would be an endothermic reaction. So endo means in, therm means heat, so heat going in. So endothermic reactions require an input of heat to proceed. Okay, so exothermic reactions will release heat. Endothermic reactions will require heat input in order to proceed. So we have talked about state functions, and we've also talked about exothermic versus endothermic processes. In the next lecture, we will talk about the first law of thermodynamics.